In this video, we are going to solve a system of linear equations using the substitution strategy. So previously, we learned how to solve a system of linear equations using the graphing strategy. And when we used that graphing strategy, what we did was we graphed the two lines on the graph and we looked for a point of intersection. And for all of the problems we've done previously, they would typically cross at a really nice coordinate point. However, if we get an example like this, so see how these two lines aren't crossing at a nice point, it's difficult to determine that point. So it's difficult to determine that point accurately. So essentially what we need are other strategies that will allow us to find what that point is, even if it's not a nice point. And that's what we're going to start to cover in today's video. And we're going to use a strategy called substitution in order to do this. So the substitution strategy is an algebraic method that is used to solve a system of linear equations. And it's typically used when we can easily rewrite one equation for one variable alone. And typically this means that we can do it in one single step. So what I mean by this is if we look at these two examples down below, what we'll notice in this first example is we have two equations with the same variables, so we know it's a system of equations. And if I look at the four variables, so here I have x in the first equation, y in the first equation, x in the second equation, and y in the second equation. What I notice is that I could easily get this x value right here alone if I just subtract 2y from each side. So I can get x by itself in one step, and this will say x is equal to 7 plus a negative 2y. So when I can get one of those equations written in terms of one variable by itself in one step, this is when substitution is a great strategy. If we look over at the next example, so here we have equation 1 and equation 2, what we'll notice is again we have four variables. So we have x in the first equation, y in the first equation, x in the second equation, and y in the second equation. And what I notice here is if I look at the four variables, I could get this y in the first equation by itself really quickly in one single step if I were to add 2x to each side. So we would have y equals 3 plus 2x. So if you notice that you can rewrite one of those equations for one variable alone in one single step, that is a situation where substitution is going to be a good method of choice. So these are the 5 steps we're going to follow when we solve a system using the substitution strategy. And I'm not going to break them down right now, but I just want you to look through them and notice that the first thing we're going to do is we're going to solve for one variable alone. So that talks about the previous slide where you can easily get x or y alone in one of the equations. Then what we're going to do is we're going to box it up and we're going to substitute it into the other equation. We'll then have an equation with one variable so we can solve for the first variable. And now that we know the first variable value, we can substitute it into the original equations, find the other, and then we'll write our final answer as an ordered pair. So now we're going to walk through those same steps. Our first step is we need to solve for one of the equations for x or y alone. And when I look here, what I notice is I actually have two options. I could either solve for this y alone in one single step by adding 3x to each side, or this x alone by subtracting 2y from each side. And it ultimately doesn't matter, we just need to commit to one. So for this particular problem, I'm going to commit to the y. So we're going to get that y value that I have circled by itself, and we do so by adding 3x to each side. So essentially what I've done is I've taken that first equation and I've rewritten it for y equals 2 plus 3x. And then what I note here is that y is equal to 2 plus 3x. And remember, an equal sign means that they are the same value. So what this means here is that y and 2 plus 3x regardless of what their variable values are, y and 2 plus 3x have the exact same value. So what I can do is I can actually replace y with its equivalent, which is 2 plus 3x. They are the same thing. So what I'm going to do here is I'm going to box it up and say, well, y and 2 plus 3x are the same thing. And I'm going to substitute it in for y in this second equation. So I'm going to rewrite the second equation, and as I do that, I'm going to replace y with what it's equivalent to, which is 2 plus 3x. So here we have x plus 2. I'm replacing y with something it's equivalent to, which in this case I notice is 2 plus 3x. And notice I'm putting it in parentheses there to say this is all going in place of y. So notice I have this exact same second equation here. All I've done is replace this y value with something that it's equivalent to, which is 2 plus 3x. But what's really nice here and why we can use substitution is if we look at this equation now, we'll notice that it only consists of an x variable. So what we now need to do is we need to solve this equation for x. And the first thing I notice is that it contains parentheses. So I'm going to start by distributing the 2 to the numbers inside. So I have x plus 4 plus 6x is equal to 11. I then notice that I have like terms on the same side of the equation. So I have 7x plus 4 is equal to 11. I then want to get the x alone, so I subtract 4 from each side, and I end up with 7x is equal to 7. Divide both sides by 7, and I find that x is equal to 1. Now remember, when we're solving a system, we are finding a point of intersection. So essentially what I found here, when I find a point of intersection, when I find my x value, in my ordered pair, I have found my x value is 1. And now what I need to find is the y value that pairs with it. So what I'm going to do is I'm going to take that x value and I'm going to substitute it back into one of these two original equations, because those two original equations have the same x and y point where they are crossing. So what I can do is I can replace x in one of those equations with 1 and find the corresponding y value. So say I pick the first equation here. So I have negative 3x plus y equals 2. So here it would be negative 3. I know x is 1 plus y is equal to 2. So I have negative 3 plus y equals 2. I need to get y alone, so I add 3 to each side, and I find y is equal to 5. Now, I've had some students in the past who didn't necessarily believe me that you could pick either equation, so we're going to try this second one just to make sure we get the same y value, the same point where they cross. So here we have x plus 2y equals 11. So here I have 1 in place of the x because that's what x is equal to, plus 2y equals 11. Subtract 1 from each side. We get 2y is equal to 10, divide by 2, and we find y is equal to 5. So notice that regardless of the equation we use, we get the same y value because this is the point where these two lines cross. These two lines cross when x is 1 and y is 5. So again, I'm looking to use substitution here, and if I look at my two starting equations, what I notice is that this y value here would be very, very, very easy to get alone. And this one might be easy to get alone. I would just have to deal with that negative 1 out in front. So I'm looking for variables that I can get alone in one step. And the easiest one is going to be the y value in that first equation. So I'm going to focus on getting y alone here by adding 4x to each side. So I end up with y is equal to a negative 4 plus 4x. And then what I'm going to do is I'm going to box it up, and I'm going to replace y in the other equation with what it's equivalent to, which is negative 4 plus 4x. So I'm going to replace this y here with its equivalent of negative 4 plus 4x. So now I go down to step 2 and I actually replace y in this second equation. So I have 3x minus, then in parentheses, negative 4 plus 4x, so that's all going in place of y, is equal to 2. And then from here I notice that I have a negative number in front of the parentheses, which is really a negative 1, so I'm going to utilize keep, change here. And then in order to solve for that first variable, I'm going to distribute that negative 1. So here I have 3x, negative 1 times negative 4 is plus 4, and then plus a negative 4x is equal to 2. And then from here I notice that I have like terms on the same side of the equation. So I have negative 1x plus 4 is equal to 2. Subtract 4 on each side. And I end up with negative 1x is equal to negative 2. Divide both sides by a negative 1, and I find that the x-coordinate in the point of intersection for these two lines is x is equal to 2. I then take this x equals 2 value, and I'm going to plug it back into one of these original equations here to find the corresponding y value. So I'm just going to pick the first equation. So here we have y minus 4 times 2 is equal to a negative 4. So I really have y minus 8 equals negative 4. Add 8 to each side, and I find y equals 4. So what I have essentially found here is that my point of intersection for these two linear equations occurs when x is 2 and y is 4.